I mean, welcome. Um, Welcome everyone. Just a quick announcement first. So this talk is going to be recorded. So in case you have objections to that, you can leave now or make yourself invisible or something. At the end, we will have questions again. I mean, of course, and the questions will not be recorded. So you can save your questions to the end, or if you like, also just throw them in the chat, unmute yourself, whatever works for you. So without further ado, it's my pleasure to welcome Paul Balmer, who is giving the third and final talk in this mini-series on Motivic DT geometry, bringing everything to a conclusion and maybe beyond. So thank you very much for your time, and you have the stage. Thank you.
Thank you. So let me start by thanking the organizers, Tobias in particular, for putting that together, and thanking Scott and Martin and Scott for the first two parts. As Tobias said, please feel free to ask questions even if this is recorded. It's not recorded because I think it's going to be brilliant, but I think, I'm happy to keep some videos because I've noticed that many people prefer to learn by listening to things rather than reading. And so it's good to have some stuff available. So please feel free and comfortable to ask questions. It's not meant to be very, very broadly distributed, but anyway, so what was discussed in parts 1 and 2, very quickly. I'm not going to redo any of that, but in very simple terms, the idea was to consider a tensor triangulated category. So the homotopy category of some homotopy theory, that's for the triangulated, the stable homotopy category, in the presence of a tensor structure, and out of that to produce a space called the spectrum, the tensor triangular spectrum, of the small objects. So here we focus on the C is for compact, but typically we assume that they agree with the so-called rigid or strongly dualizable objects. Don't worry about that, just think the small objects, which is a topological space. And this topological space does a few things for you. Well, it is the source of geometry, or geometric study of T. For instance, in that objects have a support in that spectrum. And so you can say, oh, that object lives over here or lives over there by thinking of different parts of the spectrum and compare where a different object lives and stuff like that. Related to that is that this theory of support is very good for the small objects. So it classifies the objects of TC, so the small ones, not up to isomorphism, because this is not just a category, it's a tensor triangulated category. So up to the tensor triangular structure, what can you build from one object? So that's one of the, what can you build from an object with tensors and triangles and stuff like that? And this is done, the classification is exactly through the support that I mentioned just a moment ago. And you can also think of it as a generalization of the chromatic homotopy theory, chromatic theory in topology. And what I want to do today is tell you a little bit about what we know, or rather what we don't know about the Motivic setting. And it is actually, so it's a general philosophy to try to change the tensor triangulated category, to another setting, say in algebraic geometry or in representation theory, or you name it, and try to say, well, can you compute the spectrum, and can you use these ideas to say new things about this tensor triangulated category? And it is a major open problem in this field of tensor triangular geometry. It's a major problem is to compute spec for so-called Motivic tensor-triangulated categories T. Okay, so let me explain a little bit what I mean by Motivic. A Motivic, which is sometimes referred to as A1 homotopic, so it depends a bit on the emphasis. Motivic theory, but they have things in common, and essentially what they have in common is you start with a kind of a wish list, and you change a little bit the realization of your wishes. So let me present it a bit like that. So you have a wish list, and the wish list is that you want to do a homotopy theory of algebraic varieties. So you fix a field. I'm going to call it F, and for many of the things I'm going to say, it's better to assume it's perfect, so that every finite extension is separable and of characteristic different from 2. And what you want is a world in which every variety over F, or every smooth variety perhaps, every X in smooth over F. So this stands for the smooth varieties over the field F. You want to gives you an object, and this object you can call the motive of X. And you might put an adjective before motive, depending on which type of way you realize the wish list. As you are going to see in a moment, there are different flavors. And what you do, what you want is, as I said, is you want the homotopy theory using A1 as an interval, but you should keep track of the geometry. So you have a geometry, the algebraic geometry. We have a geometry on smooth schemes in the form of a Grothendieck topology. And so the most important one is probably the Nisnevich topology. I'm not going to explain what the Nisnevich topology is. It would take a whole talk. Or the Étale topology, and in some situations the Zariski topology, I suppose, although the Nisnevich one has been the most useful. And then you impose that A1 cross X, the projection, if you want, of the affine line over X should be an equivalence, an isomorphism. You want to impose that. So it's another way of saying that if you have a family of things, of varieties, depending on the polynomial and you on a variable, and then you evaluate this family at 0 and at 1, you consider two things to be the same. So in algebra, you cannot really realize the interval 0, 1. You would have the interval 0, 1 is not an algebraic variety. So you replace that by the whole line. So that's one way of thinking of it. And then what you do, there is another thing you have to do, but the source of the tensor will be coming from the Cartesian product of varieties. So the tensor should be such that the motives of X cross, tensor the motive of Y. I would have to be a bit more careful here and call the motive call it maybe X with a little plus down here, so a little plus here. So you want that to be the Cartesian product of varieties. So you want to think of the tensor structure as induced on this new world that you try to create from the Cartesian product of varieties over F. And finally, there is something that hopefully the equivalent homotopists among you, if there are some, will recognize, is that when you do something like that, well, first in topology, when you work up to homotopy, there is another step after that, which is to try to work stably, and it makes everything a bit nicer because it becomes an additive category, it becomes an actual triangulated category. So you stabilize, but you don't only stabilize with respect to the kind of the naive homotopy theory, you stabilize by inverting an algebraic circle, which is P1. And when I mean P1 here, I mean a reduced form. So not the P1 with the disjoint base point, but the one pointed at any point that you choose on P1, say 0, something like that. Okay, I don't want to go into the subtleties of having a disjoint base point or the pointed story. It's something like very standard, the way you do it in topology. You would not expect the smash product of pointed things to be just a Cartesian product, except when you take a disjoint base point. And so you can arrange things like that. So this P1 is a bit surprising, and I'm going to come back to that in the next discussion, okay? But now how to do, I'm going to take questions in a moment about this general setting, but I would like to make it a bit more concrete before taking questions, because otherwise you would have questions about what do you even mean here? And let me try to explain what I mean, okay? So how do you do that? Well, there are many ways of doing it, and there is let me try to distinguish at least 2 ways. Maybe I'll call that the algebraic, the topological way, and the algebraic way. And it is in what one could call the coefficients. So you take coefficients in topology, you would take coefficients in category S of spectra, or you can think simplicial sets, and you take coefficients here in, well, you could think a abelian group, or if you have a ring, you can take a chain complex in the ring, or a commutative ring. And typically just, the integers. And this will give us two different incarnations. This one would be what one calls the stable homotopy category over the field, the Motivic stable homotopy category. I mean, usually you could put a little decoration like an A1, especially if you're dealing with many type of homotopy categories. But today I'm just going to talk about this one probably. Well, that's not true. I'm going to talk a bit about the topological one. So, okay, if you want, you can put a little mot here to see the Motivic story. And here you would get not quite, this is a little lie, but you will get the derived category of motives of the field with coefficients in R. So here there's some small print. There is also here, this one actually also encodes transfer. And I'm not going to go into subtleties here, but there is a version very close to this one, which would follow exactly what I'm saying. So what is the link with what I was saying before? So if you start with your wish list and you look at all smooth schemes over the field, and you want to start doing some homotopy theory, this is a rather crude category which lacks enough limits and co-limits. So the standard way of doing that is to say, okay, we are going to first look at, say, all pre-sheaves in some you kind of complete it with some coefficients. So you look at all pre-sheaves into spaces or into modules or into chain complex, or you name it. So that's kind of the first step that is typically happening. The next thing you do to maintain some connection with the algebraic geometry is to force coverings to remain, to give you triangles in some sense. So it's obtained by a localization, and so is the second operation, the A1 homotopy. So these things here are typically obtained via what is called localization. That is creating new isomorphism or new weak equivalences, if you want. That step here is usually done via a technique called Day convolution, which just says, if you have a tensor, if you look at functors like that from let me take a little color here, from a category on which you have an operation like that into one which there is a way of making a tensor on all pre-sheaves, which is just by continuously completing this one. And finally, this is done by what is called stabilization. by creating spectra, not in the sense of spectra, the triangular spectra, but in the sense of spectra like I used here. That is where you invert, instead of in topology just inverting suspension, here you invert another endo functor. So there's some technology to do those things, and you will get different answers depending on which world you play with. And you can ask, well, why do we do that? You could answer that by saying, oh, you want to do a homotopy theory of varieties. That could be an interesting question in itself. But it's also like in homotopy theory, as Martin explained in his first talk, the goal is also to represent some cohomology theories. You can represent cohomology theories in the stable homotopy theory, and here you can represent some cohomology theories in this category. For instance, you can represent algebraic K theory in this category, and that has its use. And in this world here, you could this one here was, for instance, the cohomology that you have there, that you can see in the homomorphism from the unit for the tensor and some shifts for the various spheres will give you the so-called Motivic cohomology. And Motivic cohomology, you know, is an interest. It's a very important topic in this Motivic world. Okay, I probably don't want at this point to open that type of discussion because it would absorb my entire talk. But there are really strong motivation to look at those categories. It's not just for the sake of producing a tensor triangulated category. It's the other way around, right? These were constructed because you needed them, and then you observe there are triangulated categories, there are tensor triangulated categories, so you can try to study them through tensor triangular geometry. So I think I should at this point make a little break and take questions if you at least get a feeling of where we are. And I apologize for not giving very precise definitions, but precise definition would certainly take a full hour to give some. Okay, so let me try to give you some.
So sorry,
yeah,
Paul, quick. So thanks. This was a great overview. What happens if I apply this last construction just to smooth manifolds? You know, the things that other people might study. Do you just get back the good old category of spectra?
I don't know that. Perhaps someone in the audience knows. It doesn't seem impossible. Yes.
I think I remember that Duggar showed that if you take spaces, you get back the stable category, instead of algebraic varieties. I was just wondering about smooth manifolds.
I don't know the answer. It's a good question. Yeah, but I would. Yeah, I wouldn't be surprised if the answer was yes, but I don't know.
Okay.
So let me try to give you a feeling of those categories a little bit. So perhaps again, in terms of general comments, maybe let me say that while I write the title. So let me start by a first part on this stable homotopy category. So the first thing you can ask is, okay, you create a big monster through a wish list by generators and relation, essentially. And then on top of that, you're going to look at some other construction, the spectrum. What are the chances that this is not an absolute horror that we have no control of? And this, the motivation behind that is probably what happened in topology. If you started in topology with the stable homotopy category, the first instinct was probably that there was no way of classifying spaces even stably and up to homotopy, even p locally. And there was a big theorem of the big achievement of the chromatic homotopy theory. As Martin recalled you in the first talk, that it is actually not only possible, but that the answer is a somewhat simple thing. It's just, the answer is simple. The proof that it's true is not simple, but that is just a tower of subcategories, the chromatic height, and that's it. And so I would like to give you a little bit of a feeling of why we might hope that these categories are not too wild, or at least, or try to see what's their wilderness, and also at the same time try to give you a feeling of what are the tools of tensor triangular geometry that we could use in doing that. So the first thing is that, of course, the spectrum is a functor. So the first thing you might ask is, what are the tensor-triangular functor around? And there are tons of those. Okay, there are really, really lots of diagrams of tensor-triangular functors you can draw. And but let's look at the perhaps most basic one. And by doing that, I want to emphasize the fact that this category is not really replacing topological spaces by varieties. It's doing the homotopy theory of varieties, and the spaces are still there as coefficients. Okay, so here is a bunch of tensor triangular functors. One of them is just a constant. So if you think of them as pre-sheaf, it's just a constant pre-sheaf, or if you think of SHF as the Motivic stable homotopy category as being a homotopy category, it should be acted by spectra. Spectra act on everything. And so if your everything's stable and triangle stable homotopic. And so if your field, that's a condition, of course, it's not, and it's not always true, but if your field is contained in the complex numbers, then you can extend scalars to the complex numbers, and then you can do a realization whose construction is not completely obvious, but it's essentially doing something like sending smooth schemes to the topological set of the topological space of its complex points with its analytic topology. So there is a way, there exists such a functor, and all of these are tensor triangular functor. And if you compose everything, you will get the identity. This is simply because the unit of the tensor in here, it realizes to the unit here, and this is just sending a space to the space acting on the unit, so it then acts on the unit. It's not very difficult fact, except what the difficulty is in building the functors, not so much into checking that the composite is the identity. And for instance, the usual spheres here will go to what you could call the topological spheres. And they exist there, and stuff that you know from topology will still have an incarnation in this Motivic world. But as I said, there's also some geometric spheres. And so as by constructions, we have inverted P1. And you can show that P1 in the stable homotopy category is isomorphic to the usual sphere, tensor another sphere, which is a GM. So where GM is just the A1 without zero, the spectrum of K of TT inverse. And here I mean pointed at, so it's the reduced version, so pointed at one, for instance. So this is also a sphere, and to convince you that this is a sphere, you can just think of the realization. You realize this GM. So you look at the complex point of this thing, you get just an A1, so you get an A1 without zero. So if you draw a picture, a real picture, you would have a complex plane, and you just don't have zero here. So this one is removed. And so this is up to homotopy is just the circle that you have here, right? So this is just an S1. So at least from the point of view of realization, it's not so surprising that this is also a sphere. It's not a circle if you want. It's another circle which goes onto the topological circle. And that's a basic observation, which has lots of variation. The many topological constructions have a Motivic. I don't want to call it an avatar, because the avatar would be coming through the constant. So all the many topological constructions have an image through the constant functor, but they also have an algebraic variant. So let me give you an example of that also in order to build a bit of your intuition. So you have the usual Hopf map. Maybe I'll call it the topological Hopf map from 1 to S-1, so S1 inverse if you want. So how do you build that? Well, you build it stably by building a map from S3 to S2. And this S3 is just by you look at C2 without zero. So you look at the complex plane without the origin, and you look at its class in the projective line. So CP1 is just an S2, right? It's a complex line, so it's a complex plane if you think of it really with a point at infinity. So it's it's a Riemann sphere. So this is just the same as an S2, and C2 without 0, well, it's an R4 without the origin. So this one is, if you want, this was diffeomorphic to that. This is homotopy equivalent to just an S3, very much like in this picture here, but with one more dimension. And so when you desuspend, you get that guy. And so you out of that, and the constant factor, you get this topological Hopf map also in SHF. So this exists in SH, but then also exists in SHF by taking constant. Okay, but then there is also an algebraic version of that, which does really, if you think about it, just the same thing. So you say, okay, if I was looking at C2 without 0, I'm really looking at A2 minus 0, so that they are fine plane without the origin. And I want to, there is a map of varieties to P1. And then you have to work a little bit to show, and using the various things we have in our wish list, that this thing will be, well, a suspension of actually a GM square. And this will be in SH, in SHF. This will be isomorphic to an S1 in tensor GM. And so if you desuspend, say that number of time, you see that you have to go down by one GM here. So you get an algebraic eta, which is not going to go from the unit to the circle inverted, but to the GM inverted, to the algebraic circle inverted. And this guy lives in SH, and it realizes when you realize it down. So this is in SHF, and when you go in SH, it will also go to the classical topological. Just because this picture here realizes onto this one. So you will get the an algebraic version of the Hopf map, which is which realizes to the topological one, and which is different from the topological one simply because it lands in different spaces, that different grading, if you want, in terms of those spheres. But also it is substantially different in that it is not nilpotent, whereas the topological Hopf map to the fourth power is 0, the fourth tensor power is 0, but the algebraic one is not tensor nilpotent. That's a result of Morel, that the algebraic eta is not tensor nilpotent, is never tensor nilpotent, I should say. It's not for some field, but it's never tensor nilpotent. And in fact, this is part of a broader work of Morel that shows that he computes the whole homomorphism from 1 to all the powers of GM, and he gets what we now call, that he baptized the Morel-Witt, not the Morel-Witt, the Milnor-Witt K-theory. Sorry, I'm getting a bit tired. And I'm going to talk about that also if I have time. I'm getting a bit nervous about my time management here. But anyway, just if you have an intuition about those spectra and you think that those spectra have something to do with the spectrum of commutative rings, when you have an element which is not nilpotent, it tells you something geometrically. So the corollary of that is that if you look at this tensor-triangular functor, so I did not follow through my motivation here. I said these are tensor-triangular functors, so they will all induce stuff on spectra. They all preserve compact objects. So the map on spectra will go backwards. The spectrum is contravariant, like in commutative algebra. And so you see that you have a copy of the chromatic spectrum, the one which gives you chromatic homotopy theory, inside it injects inside the Motivic version, at least when the field is contained in the complex numbers. You can think the complex numbers themselves is interesting. And you might ask, well, perhaps we are very lucky, and perhaps that's just the same. Perhaps this whole story about introducing varieties will not make the chromatic story different. And in fact, they are different because of this algebraic. I mean, it's the first thing we saw about the difference. And it says that if you do spec of the realization from spec, so here I'm assuming the field is contained in So this will be injective. I'm assuming the field is contained in the complex numbers into the Motivic spectrum. I'm sorry for that. The spectrum of the Motivic homotopy category. That's an it's a split injection. This one, as I said, is a known thing. It's the Hopkins-Smith story. This one is the mysterious one that we're after. But what we know is that this is not surjective. And in fact, what you know is that the image is entirely contained in the support of the cone of that map, eta algebraic. That's in some sense, in tensor-triangular geometry parlance, this is the locus where eta is nilpotent. Eta algebraic is nilpotent, so it has to live only in the locus where eta algebraic is nilpotent. It cannot live everywhere. And this is the support. You can describe it as actually the support of a certain variety, just P2. And I proved that in a paper in the spectra paper on constructing the comparison map, which I'm going to mention in a moment as well. But at the time, it was not clear if this was sharp. Maybe that's it. Maybe everything in this support of the cone of the algebraic Hopf map would be coming from topology. And well, there is some stuff in print which is incorrect. Actually, people have claimed that this is a strict inclusion, and I think it was formally open until yesterday, and I think if the discussion I had with Martin are correct, we now know a proof that this is a sharp inclusion. So there is more to it, and in particular, I suspect that the realization will not catch the close points of the Motivic, of the spectrum of the Motivic homotopy category. And this is actually a good segue into the second part of the talk, which is about the algebraic version, because this information, that this sharpening of this theorem here is through the Motivic derived category of motives, the DM that I mentioned before. Let me just mention here, and perhaps to save a little bit of time, instead of writing down everything, I would just point to a very interesting reference to work of Jeremiah Heller and Kyle Ormsby, who showed that the comparison map, so I'm going to write it very telegraphically, but that the comparison map is onto. So one of the very basic idea, which already exists if you want it in homotopy theory, is to say, okay, you have this big SH. Is there a fundamental organization of things? And in homotopy theory, the fundamental organization is just to localize one prime, one classical prime at a time. You localize at 2, at 3, at 5, and so on. And the key point here is that the endomorphism of the unit object for the tensor is the integers. And in a general tensor triangulated category, you have an endomorphism ring of the unit object, which is a commutative ring, might not be the integers. And in that case, and then you can fiber the whole spectrum over the spectrum of the endomorphism. So I think Scott ended up with this explanation last time. So the spectrum of TC, let's say, and you can look at the usual Zariski spectrum of, well, you can go all the way down to the usual Zariski spectrum of the endomorphism of the unit. Here's a commutative ring, and you can do graded versions. So this is the comparison map row, and there is a version where you take U, a tensor invertible, like a circle, like the GM that we have here. So here it's for U equals GM, and you can look here at the graded endomorphism, or let's say the ring where you have the homomorphism from 1 into the tensor powers of your invertible. That gives you a graded ring, and you can ask, well, is there a relation between those two things? And what they proved in this paper is that this map here is surjective. And as I said, by Morel, we know this endomorphism ring here. This is Milnor-Wittke theory. But I think that would be a digression at this point. So let me cut that just to save a few minutes. Okay, so the second part of what I want to say is about more linearized stories. So in the case of DM, and again, let me make a short break here to take possible questions. Yeah, I don't seem to be able to make a little square, little rectangle. Yeah.
So are there algebraic versions of the other Hopf maps?
Yeah, okay, so that's the first thing. In DM, there is no homomorphism to the negative powers of GM that will go to zero. So there is a linearization. So there is a TT functor. Did you say algebraic or linear versions? Maybe
Algebraic version of, like, you know, S7 to S4 or something like that.
Oh yeah, I would guess. Yeah. There is a whole zoo of those Motivic. I mean, the whole study of those Motivic stems and the stable homotopy groups, and it's a very difficult. It's very difficult in homotopy theory, and it's also, you know, it's even harder in Motivic story. So there's the whole cottage industry of people studying those things, and there's an abundance of those, and more complicated one, though, some which exist really just in this world and have no interesting incarnation in homotopy. Maybe let me see. I might have time to mention, you know, the bot element. I'll see. I might give one in a moment, but the answer is yes. There are lots of those. But I misunderstood your question as is what happens to the Hopf map under this functor, which would be the linearization. And that's also an interesting question, but except that this goes to zero simply because the Hom groups in which they sit are zero. There's no Hom to the negative weights in DM. So eta will not be that interesting. The graded endomorphism, in fact, in that case, in that case here in the DM, the endomorphism from the unit to GM tensor N, that is just the Milnor K theory of the field. So that's for, if you want, for N non-negative and 0 for N negative. So it's actually just exactly modding out by eta. The relationship between the Milnor weight and the Milnor K theory is exactly modding out by eta. So on the endomorphism ring, it looks like it's exactly modding out by eta. So Milnor K theory is perhaps something more classical. I would expect more of you to know what this is, right? It's just the free tensor algebra on the units of F, where you mod out by you want the product to be the sum of the representative, so the units are in degree 1, and the Steinberg relation that 1 times A times 1 minus A should be 0. So that's more classical object, and in fact, if you look at, there is also a grading by the shift in DM, and so if you combine both, you get exactly Motivic cohomology. So Motivic cohomology has 2 gradings, one by shift and one by weight, which are essentially one by shift, the suspension in this triangulated category, the smashing with S1, and the one with GM. There is up to some conventions that I won't go into. So okay, let me perhaps start with the rational story. So what if R equals Q? So rationally, what do we expect? Well, rationally, the picture is rather hard to solve. It's known only in very few cases, but it's conjectured by several people that the spectrum of the geometric, so the compact is usually denoted with GM for geometric, but let me write just compact. Now that should just be a point. And now you should be careful, because if you're new to that, you might be forgiven for thinking, oh, that's boring. It's just going to be a point. So it's But if you know a bit about the topic, you appreciate that as a very strong, it's a very strong statement, right? This category, which could be a monster, has only a point as a spectrum. And this conjecture implies a sequence of very deep and complicated conjectures in the Motivic world. In fact, it implies the so-called, for those of you who know, I'm not going to explain what this means, but it implies the so-called conservativity conjecture. Conservativity conjecture, which says that étale realization is conservative, conservativity conjecture. And it's actually almost equivalent to it. It's a strong form of the conservativity conjecture. And there's a nice paper by Martin, which appeared this year in the Bulletin of the LMS, where he shows that how, if you have all the standard conjectures of the Motivic world, you would get that. Okay, so it is conjectural, but it sits very nicely in this gigantic net of conjectures, which because of which maybe motives are famous. If you have heard about motives, you've probably heard of tons of conjecture around that. So you can ask, well, let's look at integrally. So integrally, you can say, because of this, you can say, well, essentially, we are going to assume that rationally it's a point, and the story is really, so the complexity is really related to the case of the Z mod P coefficients. Okay, so studying the spectrum integrally or with mod P coefficients is a similar level of complexity if you believe the conjecture about the rational thing being just a point. Okay, so by the way, I should maybe mention that this functor here is actually known to be conservative on compacts for some fields. I believe it's maybe those where -1 is the sum of square or something like that. It's a result of Tom Bachmann, 2018, if my notes are correct. And so, for instance, it would be conservative on compact for the complex numbers. And the fact that the TT functor is conservative on compacts has a meaning in the spectrum. It means that the map on spectra, on the tensor-triangular spectra, is surjective on closed points. So it means that the spectrum of this thing here, which might be very complicated, at least its closed points, the maximal primes, if you want, it's not quite, it will be the minimal ones, but the closed points in the spectrum will be all coming from the linearized version. Very much like in topology, the closed points in the chromatic story, they come from cohomology with finite coefficients, cohomology in Z mod P. And so it's a similar story which happens here. And that's a way to prove what I said before. That's how we should be able to show that this is actually missing the closed points. Okay, so let me not go in circles, but try to be a bit systematic. So what do we know now with integral coefficients or finite coefficients? Well, as I said, one of the tools is to use the comparison map. So let's look at the comparison map that Scott explained last time. So if you look at this comparison map again for the invertible being GM, which is still invertible in here, to the homogeneous spectrum of the, let me write endomorphism, the U endomorphism of the unit, right? So in this case, this will be surjective here too, in the integral case. But if we describe those endomorphisms, so just the endomorphism of the unit will be, if you want, it's pedantic terms, it's Milnor K theory in degree 0, but it's just integers. And as I said before, the endomorphism will be Milnor K theory of the field. And maybe let me see with time, I would like to give you, so the spectrum of that is known. It's a bit more complicated than what you have in topology, but it's not that much complicated, that much more complicated. So let me give you an example. So if the field was the complex numbers, for instance, the spectrum of that thing, everything in positive degree would be nilpotent. And so the spectrum would just be the spectrum of the degree 0 part, which is spec Z. And if the field, let's take a slightly more interesting example, which will connect to what I hope to say in the last 13 minutes. If you take the field to be the real numbers, then the spectrum of Milnor-K theory, yes. Well, it has the spectrum of degree 0 part, so it has the spectrum of Z if you want. Always with the irrelevant ideals, so with all the positive degree elements. It has the, so this is a picture of the spectrum of Z. You have the usual primes and 0. So let me call that P0. As I said, this P0 is just the irrelevant part, so it's K positive of N, K positive of R. And the amusing thing is that there is one more prime, which sits, so the lines indicate that the point is in, the higher point is in the closure of the lower one. So it's the specialization relations, if you want. There's one more prime here, which I'm going to call refer to as the amusing prime, because we are going to see that come back in a moment. So just to have a name for it, okay? So, and this amusing prime is obtained by, in the Milnor-K theory, you can describe it pretty easily. It lives at 2. So if you send all that down to spec Z, spec of the integers, those 2 points here would go to 2. So it is generated by 2, but you don't take all the positive part of the Milnor-K theory, you just take the ones of positive elements. And in general, when you have a field, you will have a similar picture with a few amusing primes for all orderings on your field. Here you have only on the real, you only have only one, so where you take A positive. So you look at this ideal, and this ideal is contained, of course, in the one generated by, oh, I didn't explain very clearly what this is the one generated by P and P0, if you want. So this is generated by 2 and all the positive, all the elements in K1. So of course, this one is contained, you have this inclusion here. And if you want to really check that, you can give a residue ring, which is a domain. You can do this exercise. It's an amusing exercise on the standard relation. Let me not go into that. But you can check that the spectrum is like that. So it's very close to, this part would be a spec Z, so to speak, the usual prime. But there is this amusing kind of exotic prime which lives above the prime 2, the usual classical prime 2, but in that ring is relevant. So in some sense, if you study things, so this tells you that if you look at the spectrum of D M of the real numbers with integral coefficients or with mod 2 coefficients, right? Because probably this is going to happen at 2. This should have something amusing at 2. Should have something interesting at 2. Okay. So another variation you can do on this theme of motives, and this will be my third part, is to do variants of DM, so simpler variants. So that's another idea we can really, I mean, as I said, the theme of the talk is that we don't know anything definitive on the Motivic, on the spectrum of those Motivic homotopy categories, but we know lots of information and we try to make organize those things together. So at the moment we don't know what the spectrum of DM will be, but you can construct things in it, smaller categories, or you could call them cellular categories. You could say, oh, you have those spheres there. Why don't you build some the smallest category that they generate, that those spheres generate. So this would be called the notation is DTM, the T is for Tate. And this is by looking at, so all the examples I'm going to describe here are all the examples I'm going to describe here will be the TT subcategories generated by some objects. And so in the case of T, you take just the spheres, the GM. But you could also say, well, what about forgetting GM and say you have a field F, and you could look at something we could call the Artin story. So in the case of A, what are the things you take as generators? You say, let's look at all the finite extensions of the field. These are smooth. These are smooth varieties of very simple type. They're just dimension 0 smooth varieties. So that's an amusing class of varieties you can look, and you could say, well, what do they generate? And maybe this will tell you something about the whole thing. And you can combine the two in the Artin-Tate. These are the Artin-Tate motifs. So this is for Artin, and this is Artin-Tate. And they all live in here. And what is behind that is the fact, which was also mentioned in Scott's talk, that if you have an inclusion of tensor triangulated category, if you have a K inside L, these are for small ones, right? And the K is rigid, that's a technical condition that has to do with the tensor, but all our examples are. Then if you look at the map induced by spec L back to spec K, it is surjective. So it means that maybe you don't know what spec L is, but everything you see in spec K, everything you create in those subcategories must come from something in the big category. There must be some geometric things happening in the big category that will reflect the things you create in the small one. So there are partial information in the sense that we only study subcategories, but every information you get there means there is something like that which will live above it in the big category. Okay, so that's another type of thing you can, type of lines you can pursue. And you could also change. I have said almost nothing about the topology. You could also change the topology to the étale topology. So the DM étale. This will open a bunch of complications, but there is a very remarkable fact that for the étale one, the story is essentially known by work of Martin, at least in the algebraically closed case. So in the case of the complex numbers, for instance, I'm not sure I will have time to discuss that. So let me perhaps leave the étale part on the side and focus on the left hand side. So but again, if I wrote cheesily without saying it out loud, like a localization symbol or something like that. It's very close to a localization, so it's very close to the spectrum of that embedding into the spectrum of this. Okay, but let me not go into that. So what about these Artin-Tate motifs? What can we say about them? And in fact, it's the first complete answer that was ever obtained in this Motivic story. And it's a theorem of Tobias Peter, who was a student of mine and who did that. The paper is published in 2013. He proved that the spectrum of Artin-Tate or Tate, it doesn't matter because we look at algebraically closed field. So you look at the closure of the rational. And with rational coefficients. So in that case, he proved that this is a point. And so that verifies in some sense the conjecture, at least for Q bar. That was the first computation. And I put that on the map because it's the first time I give you a complete answer instead of saying, here's a relation with something else and something. And we had to wait quite a while, and really that's the breakthrough of Martin it was published in Compositio in 2019 to get the answer for with finite coefficient, to get the first case with an answer for finite coefficient for an algebraically closed field. Let's say, think the complex numbers, but an algebraically closed field in which P is invertible. If you take coefficient Z mod P and P is invertible in the field, say think characteristic 0, no restriction on P, then you get 2 primes. And those 2 primes are one in the closure of the other, so Sierpinski space if you want. So we have E and an M, and the M is for Motivic and the E is for étale. And so the E is obtained as the kernel of the étale realization, and the M is obtained as the kernel of étale cohomology, and the M is the kernel of Motivic cohomology with Z mod P coefficients. So these are the very first complete answers. And using that, Martin could prove that if you look at the spectrum of DTM, so same F as before, and let's pretend that, okay, let me say it this way. So what happens is you have something like a spec Z, so you have an M2 and an E2, and you have an MP and an EP, well, only for those P's which are, invertible in the field. And then you have what we guess is going to be a point, but that's a conjectural point, okay? And it looks like that. So it looked like just spec Z with just a little bit of chromatic refinement. In the chromatic case, you have a spec Z, and at every prime you have a whole tower. Here you have just two, length 2 little refinement like that. And so if you, just to give you something I've done, let me tell you of a result that we have done for Artin-Tate motives. So it's a theorem that now this, so Balmer and Martin Gallauer, the preprint is from 2019, but the paper is not yet accepted, but I believe it is correct. So if you look at the spectrum of the derived category of Artin-Tate motives, so it's really the first in the simplest version of the Artin story. Here, the Artin story, it will just amount to the complex number, right? It's the only finite extension of the real numbers. So if you look at the Artin-Tate motives over the real numbers, what happens is, well, let me shamelessly get this and paste it here. So you will have whatever happens over the complex numbers, which will be a copy of this. The complex numbers are covered by this story. And then if you try to relate the real numbers and the complex numbers, you should not be too surprised that away from 2, there won't be a problem, because away from 2, the complex extending scalars to the complex number will be faithful and everything. So you can prove that's that, and that all the fun will happen at the prime 2. And so at the prime 2, you will have something a little bit like the amusing prime that you see on the endomorphism of the unit, on the commutative ring, which kind of sits below that. So you have this. I live in a small village in Switzerland where you hear the hour being on the clock. So I don't know if you heard the ring, but it's the end of my time. So let me just give you the statement. What happens is that we found 4 more primes. So there are 4 more points. They are related like that in terms of specialization, and they have interesting Motivic explanations. And you might ask, well, which one will go on the amusing prime? Well, actually, you can check that these are those 2 going to the amusing prime only, and that the other 4 here go to kind of the classical prime 2. So, and just to say a word about the techniques, I'm not going to say, of course, anything beyond this point, but just the techniques use modular representation theory, actually of a very simple group of the group C2. You might say, well, isn't that a bit an overkill? Well, we have to look at filtered representation. So it's not completely trivial. The representation theory with coefficients in Z mod 2. So over 2. And so that's kind of an essential ingredient. Let me say, if you want to hear more about that and about further things that I had no time to say, we have some results on in the case of the field being a finite field. So we also have the full complete answer in that case. I would like to finish by plugging some events. So you could watch tomorrow's talk by Martin at a seminar which is online, which is called New Directions in Group Theory and Triangulated Categories. And interestingly, so this is happening tomorrow, Tuesday. And so you can Google that and you will find the link. And this series had a very nice talk on October 26th. Let me go full circle in the nepotism. October 26th, there was a very nice talk by Scott, who talked about a variant of this spectrum which aims at classifying big categories, smashing subcategories of the big category. And the talk, you cannot go back in time, but the talk is on YouTube, so they do post the recording. They do record their lectures, and they post them on YouTube. I'm not sure Martin's talk will be recorded, so try to be there in person tomorrow. Okay, so well, in conclusion, I just want to say that this illustrates how tensor-triangular geometry touches a bunch of different areas, right? Homotopy theory and algebraic geometry and representation theory. I didn't have time to explain how representation theory comes into the picture, but that's really a very important ingredient. And it's also what Motivic theory does, right? It touches algebraic geometry, homotopy theory, and representation theory, and this is a very nice interaction that I invite all those interested to try to pursue with us. Thank you for your patience, and sorry for going a bit over time.